Do the garden hose analogy. Okay, I'm going to go over the garden hose analogy again. Listen very carefully. How many of you guys like going off-roading and getting mud all over the tires and the side of the car or truck or whatever? All right, a couple of you, good. When you're done and you want to make it pretty again, if you want to make it pretty again, you might take a garden hose, yes? Are you going to have no nozzle, no thumb over the end, and just turn it on full blast and be like, yep, I'm going to get this clean real fast? No. You need to increase the pressure. Look. Okay? We have volts is the pressure, the force. Amps is the flow. That's the amount of water, right? With electricity, it's the amount of what? What is flowing with electricity? What things, more specifically, what subatomic particles are flowing through a conductor that amps measures? Electrons. The amount, the sheer volume of electrons, we wouldn't measure it in volume, but again, the water analogy, right? How much water, how many electrons are flowing? That's the amps. That's the current. I like the word current because we do use that in both water, right, and in electricity. So think about the garden hose. If I want to do the work with a certain amount of power of cleaning up the vehicle, I want flow and pressure, right? So I'm going to have a nozzle on the end of that hose to increase the pressure, because with more pressure and flow, I have more power. In electricity, watts measures the power. If you've got an appliance that you want to do some work with, if you want to do more work, you need more power. So that electrical circuit, you'd want to be able to produce or provide more flow of those electrons under higher voltage, because volts times amps, the product of that is power in watts. Okay? Another example would be rivers. So in rivers, compare, for example, the Salt River, right here local, versus the Mississippi. Okay? Which of those two flows with more current, more amps, more water? The Mississippi for sure. Okay? But, especially certain portions, but on a whole, on average, the Salt has a higher elevation change over a shorter run, rise over run, right? Slope. So it has higher pressure. Okay? Some rivers, including the Salt, have areas where the water has to navigate through obstacles, right? And you might even see some white water, right, where it's really kind of rolling through the obstacles. When it's doing that, it's encountering what? Ohms, which measure resistance. So that water is moving through resistance, so it's increasing the pressure. Okay? In a battery, voltage, force, pressure comes from the differential from one side of the battery, the terminal, to the other. So when the electrons are leaving from the negative side of the battery, if the battery is fully charged, there's going to be a strong attraction to the positive terminal. So they're going to push through the circuit with more voltage, with more force. As the battery is drained, the voltage drops, and then there's going to be less force pushing, less voltage pushing the electrons from the negative terminal to the positive terminal. Therefore, less work can be done. Or if that appliance is still asking for, still pulling that wattage that it needs, what would have to increase if the voltage is decreased? If volts are decreased, the watts are still pulling the same, amps must go up, which means your wiring might start to do what? Does that help maybe with the understanding of the relationship between volts and amps and watts? And to an extent, ohms. We're going to do another problem here in just a moment. All right, number 1 says, calculate the power in a circuit having a resistance value of 10 ohms and a current flowing through the circuit at 5 amps. Again, you need to know what power is measured in. What is it power measured in?
What?
I've got 3 different answers. Look, context clues, guys. If it says calculate the power and it's giving you ohms and it's giving you amps, then power can't be measured in ohms or amps. Did I just give you guys a whole speech about how you clean the vehicle, the mud? If you have more volts and more amps, it'd give you more power, and power is measured in watts. Ah, volts! Watts! You did it on purpose. Yes! Yes! All of the answers are in watts. All right, calm down. Yeah, you were wrong? Wait. I can wait. I don't want to wait too long. Okay, so how do we do this? We're given the ohms and we're given the amps. Which formula has ohms and amps that we can use? The second, the Ohm's law formula has ohms and amps. But the answer is in volts, and our answer we're looking for is in watts. How on earth would that help us? It's a 2-part question. You've got to plug it in. So, amps times ohms gives us the volts, and then we can put the volts in this formula times the amps to get the watts. Does that make sense? Yep. It's like a step-up thing, all right? It's like a puzzle. You need to solve this little part of the puzzle to know what the, whatever. So what is ohms times amps? We've got 10 times 5. 50. So now we've got 50 volts times 5 amps. What's 50 times 5? 250 watts. Duh. Okay? Duh. Duh. All right. How many of y'all got that one right? Good. Excellent. How many of y'all got it wrong because you were like confused which one to use? Because it didn't have watts in it, right? On there, but then the other one had watts, but you didn't have the volts, so you couldn't do it. All right. Next. This one is, guys, number 2 is abstract. Okay? We're going to see how we do. And I'm going to show you how to make an abstract problem like this more concrete, all right? The question says, there we go. In an electric circuit, ready? In an electric circuit, what happens to the current flowing through the wire if voltage is reduced by half and the resistance of the wire is doubled? So voltage goes down by a half, resistance is doubled. What happens to the current or the amps? Doubled? I got one that says doubled. Doubled?
I think. Oh wait, yeah, double.
Halved?
Well, I don't know. We've done this question before, haven't we? Yeah, this is like what we did out of the book, right?
Very similar.
So I think either.
All right. Shh. What do you think?
I think it's D.
You think it's D? Okay. So listen. Listen and watch. So we have our Ohm's law here. Volts equals amps times ohms. That's the relationship you're looking at. Think mathematically now. If we drop the volts by a half and we're doubling the resistance, okay? I say again, if the ohms are being doubled, but the volts are going down, in order for the volts to go down, if the ohms are being doubled, the amps must be going which direction? Down. By enough to compensate, more than compensate for how much the ohms are going up. So the answer would be A, 1/4. Now hold on. Shh, stop. That's abstract thinking. You're kind of outside, you're not assigning numbers to it. You're saying doubled or tripled or halved or. Let's make it concrete. Okay? How do you make it concrete? What numbers? All right, so we're going to take Ohm's law and we're going to put numbers in it. Let's just say 4 volts. I need to change markers. All right. So we're going to take 4 volts and we're going to make it equal to 2 numbers that when multiplied by each other, hello. We're going to make it equal to 2 numbers that when multiplied by each other makes 4 volts. Okay? So what times what could equal 4?
2 times
2. 2 times 2. So 2 amps times 2 ohms is going to make 4 volts, yes? Okay, now let's run the scenario. If volts are cut in half and ohms are doubled, we're solving for amps. What happens to the current? So now we, again, divide to isolate the variable, yes? That, we're solving for amps. 2 divided by 4 is, what's 2 divided by 4? 2 divided by 4? A half. So, now, if 0.5 is the amperage, what is 0.5's relationship to 2? It's a quarter of 2. So your answer is a quarter. The current is 1/4 of what it was if your voltage is cut in half and your resistance is doubled.
Oh my gosh.
Again, if you struggle with the abstract, just answering it out of the top of your head, put numbers to it. Now the numbers have to work. The math has to be true, but then you can actually try what they're suggesting and see what happens to the numbers. Okay? All right. Last one, number 3. Edison, under pressure from J.P. Morgan to win the current war, used which type of current to electrocute animals to demonstrate its danger? He also invented the electric chair, which used the same current. So Edison, what you're telling me is Edison, who's heavily invested in direct current, would want to use direct current to prove how dangerous it is. He used whose alternating current?
J.P. Morgan.
Who developed alternating current? Tesla.
Nikola Tesla.
You guys are just spouting off. You don't even know what you're saying. So Tesla designed this alternating current concept, which threatened Edison, because Edison has all these patents on direct current. So he wants that to be the standard. Tesla broke off and said, I like this alternating thing that you think is dangerous. I don't think it's dangerous. Okay? So Edison, like, genuinely believed, and by the way, he's, mostly right. It is more dangerous. Alternating current is more dangerous because it's at a higher voltage. Okay? That it was unsafe. And he wants to protect his own financial interests, right? Because he has the rights to DC patents. So he tries anything he can to make AC look bad or dangerous. All right? Now, J.P. Morgan was investing in which inventor? Edison or Tesla? He was investing in Edison. That's why he was able to put pressure on him. Like, do whatever you need to do to win this because I'm invested in you. Who was the investor that was backing Tesla's AC designs? Westinghouse. Okay? Westinghouse. All right?